And for now, just allow me to switch to English, as I'm going to welcome a very special guest, one of our wonderful keynote speakers. She is the Presidential Chair at the University of Oregon and Professor of Chemistry. She is as well the founding director of COACH, which is an organization that helps women scientists and engineers in career advancement. Please, everyone, welcome Professor Geraldine Richmond.
Thank you. That's me. Can we have the slides, maybe? Well, it's great to be back. It's great to see you. This session is going to be about that amazing compound called water. And water is truly amazing. We know, for example, that it's strong enough in order to move boulders, yet light and airy enough to fly in the breeze like a snowflake. We also know that it has the slicing power to cut through stone and the ability to climb to the tallest of our trees. It also has the ability to surround us like a blanket and keep us warm, or turn on us in a moment and freeze us to death. It is water. Can I have my slides? Next slide, please. Oh, I can do it now. Great. Okay, it is water, and it's amazing, covering 70% of our planet. You know what, though? It's a really simple little molecule, that oxygen with a few hydrogens hanging on. Almost looks like a Mickey Mouse. But don't let its simplicity and commonplace fool you, for it has mysteries that we have yet to understand, and that scientists have studied for centuries. So what do we know about water? Well, we know a lot about what it's like when it's in its gas phase, when it's bouncing around, knocking off of each other. In that case, it's quite the introvert, bouncing off each other and going another direction. However, when it goes into its liquid phase, it becomes quite the extrovert. In that case, it's grabbing onto its nearby water molecules, 3 or 4 at a time, grabbing on each other in something we call, as chemists, hydrogen bonds. But for those that are not scientists, they might say that water knows how to pull on quite a rave, quite a party. Because what it's doing in that case is it's grabbing on constantly. Imagine a party, for example, where you're dancing around and everybody's dancing with 3 or 4 partners at once and constantly swapping partners. Monogamous it is not. Water is, and in fact, it's that very gregarious nature that we don't understand all that well. For example, we don't understand from a theoretical perspective how water sticks together to the most details. But what's amazing about it is that gregarious nature allows it to absorb a tremendous amount of heat or expel heat without changing its temperature very much. So think about it. While you're sitting there in the audience, your body, especially after eating lunch, is undergoing millions of chemical reactions at any particular moment. Gives off heat, takes up heat, gives off heat, takes up heat. And you're sitting there at temperature of 37 degrees C. I just find that amazing. I find it amazing. But interestingly, and even more, somewhat more mysterious, is the surface of water. Have you ever seen a bug or a leaf float on top of water? Yeah? Yeah? It's almost as if there's this very thin sheath on top of the water that's very different than what's underneath. And so what we'd like to be able to understand is how the molecules behave in that very thin sheath. To try to understand, in particular, why it has what we call a very high surface tension. So you might ask why I would be so interested in this topic for many years versus anything else. Well, one of the reasons is because water has so much importance to our planet, But also, it's a very important environmental issue. And where I live in Oregon, we are very, very serious about the environment and keeping it clean. But the second reason is I have to confess that I am a laser junkie. I love working with lasers. And since I built my first laser in graduate school over 40 years ago, I was just a baby then, of course. Over 40 years ago, I've had my hands on lasers and building them and using them in whatever capacity possible. And in this case, lasers are a great way in order to study the surface of water. So if you were to go into my laboratory with my students and postdocs, what you would find in there is a whole bunch of big lasers, and they're putting out light, and that light is then focused around the room. We have a laser focused around the room, on the table, till it eventually hits the surface of water, 2 laser beams that we reflect off the surface of water. Now, these experiments are a little trickier than they might look in this picture because, see, you can see the laser beams inside the laser there and then onto the laser table, and you can see the beams, right? In our laboratory, we use lasers that you can't see the beams because your eyes won't detect them. So you can imagine the difficulty in aligning those 20 or 30 optics once the light leaves the laser in order to get it to go on the water surface. Okay, it's even trickier than that, and that is that the laser pulses last about 1/trillionth of a second. And I got 2 beams going on, and those 2 pulses have to hit the water surface at the same time. Those pulses are separated by a longer distance of time. So it's invisible, short pulses. They got to hit at the same spot every time on that water surface. But when it works, the lasers allow us to measure the fingerprint of the water to figure out how the water is oriented at the surface, how it bonds, and how it interacts with anything in the environment that might be a pollutant, for example. So when it works, we get that information. And when it doesn't work, well, it becomes a really expensive way to boil water, which we really try to avoid. But it gives us a lot of information, and so let me tell you what we know so far about the surface of water. Remember I told you about that party going on in the bulk of water, everybody grabbing onto everybody else. Well, as water moves to the top, it's running out of dance partners because the air now is coming down and intruding on that surface. And so water has less water molecules to interact with. And so it actually changes its behavior. So within the bulk of water, the water molecules are randomly moving around, but as they get to the top layer, they take on a very different orientation. So I don't know if I can do this with the mic too. So pretend like I'm water. See if you guys can hear me. I'm water. Oxygen, hydrogen. Okay? Most of the water molecules at the surface of water, instead of being like this, they're like this, with their bonds parallel to the surface, maybe 5 degrees off axis, like this. Okay? But there are a few water molecules, and they're doing this. They got 1 hydrogen sticking up in the air. So when you look down at your glass of water, you're looking down at a bunch of hydrogens waving at you. They're like this. It's about 20%. But think about it. That makes the water surface a bit reactive because these guys are up here looking for dance partners, right? Okay? And so the surface of water is much different than we ever anticipated. But it's a combination of how it bonds and how it orients that gives us this interesting surface pressure, high surface tension, but also allows water to evaporate, right? It's got to be able to evaporate and yet be able to hold bugs on top of it or whatever you want on top of it. And so we've learned a lot with lasers about, and also theoretical work, because we do both, about what the surface of water looks like. So why is this important? So that you can be entertained when you look at your water surface and you got these thinking about these hydrogens coming up. No, it's more than that. Because when you think about it, everything that gets into your water has to go through a surface of water, right? So whether it be water running through pipes and something from your pipes gets into the water, it has to make it through the surface. Or water that's going from the soil, water that goes from the soil up into the leaves and then evaporates out every time it hits a surface. whether it's going in or coming back out again. So understanding what water looks like, not only next to air, but next to something oily or a plant or even a membrane, is important. And so whether that be something in your body where you have water or aqueous fluid running past your membranes, those membranes are kind of oily. We call them hydrophobic. But things get past that membrane. And that's what will actually be discussed a bit in the panel discussion later, things having to do with membranes, and particularly being able to take salt out of the water. And so whether you're doing some type of an osmosis process or something in your body, that water surface, you need to be able to understand it. And so that's what we do, is provide information on what's actually happening at a water surface from these examples. So I'm going to share with you now 2 examples of studies we've done over the last several years, with my students and my postdocs in the group. They're the ones that really do the hard stuff. They're the ones that are in there aligning the lasers. And sometimes when we put together a new system, it took 3 years to get the laser system to do the kind of experiments we want to do. So they're hard. But nevertheless, the students pursue it and get some beautiful results out, which I'll describe, a couple of which I'll describe now. Now, I've only chosen 2 studies, and this is like choosing your favorite children, which is really dangerous. So I'm glad none of my students are here so they can see which I've chosen to share with you. So one of these has to do with what happens with the chemistry in your air, in the atmosphere. Now, we used to think that most of the chemistry in the air happens when gas molecules bounce off of each other. Bounce off, and when they hit, they react to form something else. But now we know that most of the chemistry, including photochemistry, happens on the surface of ice particles and water particles in clouds. We call them aerosols. And so most of the chemistry is actually happening in those aerosols, those water droplets, and so forth. But as I said, anything that gets into water has to go through a surface. And so once, if you have a little droplet up in your clouds, the little droplet is up there, and some gas, for example, penetrates into that droplet. What it finds in that droplet is not pure water. What it finds is actually a chemical composition of acids that are in the air, of salts that are in the air, of organics that are in the air, that are in that little droplet and around that little droplet. And so it's kind of a chemical factory in those little droplets, some good, some bad. But what we're trying to do is understand what happens when you take a pollutant and just take not necessarily a droplet in the air, but in the laboratory, put that pollutant on a water surface and use the laser to probe what the properties are. So the one I want to describe quickly now is sulfur dioxide. Now it looks a little like Mickey Mouse also, right? However, it's a lot more pungent and it's a lot more toxic. And we know that when it glows up into the clouds and aerosols, it will form sulfuric acid. And sulfuric acid is a very strong acid. And when those clouds rain down, they rain down acid that can kill fish and acidify creeks and kill plants. So it's not good. But where does it come from? It comes from a number of different sources, one of which is volcanoes, which in my area, we have volcanoes. But it also comes from burning coal that has sulfur in it. In the United States, we have coal, dirty coal, we call it, and it has sulfur in it, and sulfur oxidizes to form SO2, goes up when it's burned, goes up into the atmosphere, and then you get acid rain. And so we've been trying to understand what happens when sulfur dioxide gets next to a water surface. Okay, so I'm going to show you some data, and I'm going to let you be the scientist and figure this out. But I'm going to give you 3 options to think about, okay? Ready for the test? Yeah, right, sure. Okay, 1, that the sulfur dioxide, as it approaches the water surface, it bounces off like a trampoline. That's number 1. Number 2, that when sulfur dioxide gets next to water, the water opens up and lets it go right in. Or 3, that the water actually goes up and grabs it and pulls it back in as its dance partner. Okay? All right. Here's the video. Here's the computer simulation. We did all the experiments, and then we verified it with the computer simulation. Please go. They promised me the movie would work. Can we have the movie? The video? Maybe I have to talk it through. Are you guys still trying, or are you giving up? One moment. Okay. Should I do like a song and dance routine? I don't know one, but I could try for the first time. If we could go back to that. Okay, so let me just at least describe what this is. So this is sulfur dioxide, as you see there, and what it's doing is getting next to a water surface. And you're going to see the big waters are just ones I've made bigger just so you can visually see them when the video goes. And then the other little water molecules are just smaller, and they're going to jiggle around once the video goes. Tell me when to give up. Don't. Oh, whoa. Okay, now you have the short version. Okay, now look at that sulfur dioxide's going down. Look at what's happening with water, right? Look at those flirtatious creatures going up and dragging it in. So actually what happens is that water goes up and grabs it and pulls it in. It's a little bit different aspect ratio than I'm used to, but just assume the water is symmetric like it's supposed to be. Anyway, it goes up and gets it, and that's really unusual. It's really unusual that water would just go grab it and bring it in. And so that tells us actually that it's a much more reactive surface for sulfur dioxide than we had anticipated. Okay, so the next, and so why is this important? Because when you're trying to understand atmospheric chemistry, it requires a lot of computer simulations. This is data that goes into a big computer simulation to predict whether it's going to be acid rain or how it's going to affect climate change or anything else. Okay, the second example that I'm going to give you is what happens when water is next to oil. Now, we normally have learned that oil and water don't mix, right? That they shouldn't like each other, that oil is hydrophobic. It means it's scared of water. And in fact, most textbooks will say that water and oil don't want to have anything to do with each other. And in fact, some theories suggest that when water gets next to oil, there's a vacuum region between water and the oil. It's very small, but it's there. But what our studies did when we put oil on top of that water surface, remember that hydrogen that was going up in the air? It actually grabs onto the oil. Weakly, kind of weak hand shape, but there's actually a little attraction between the water and the oil. And that really changes the way we think about water next to oil, because before we thought they completely avoided one another. It creates a special space that actually drags things in that you otherwise wouldn't drag it in. So why is this important? For our interests, it's particularly important because we're interested in how you can develop better things to clean up an oil spill. So as we know, oil spills can be really disastrous from an environmental perspective. They lay down on water, they can be thick, then birds get covered by them, and they're just really awful to clean up. And the normal way to clean these oil spills up is to have a plane fly over and drop what we call dispersants onto the oil. And the dispersants are to do what they're called, and that is that they are to take that oil, break it up into tiny little droplets, and that dispersant then goes around the droplets and holds the tiny droplets stable so that they then can wash out into the ocean or be eaten by microbes or sometimes fall to the bottom of the ocean. But at least it gets rid of that thick slick. The problem is that the dispersants we use today are chemically toxic. So first of all, you have an oil spill that's chemically toxic, and then you add on to that chemically toxic dispersants. Those dispersants are simple surfactants, simple soap molecules. However, the kind that they use in order for an oil spill are a concoction of a lot of different chemicals in addition to those soap molecules. So our interest is to understand if we can find biologically safe dispersants that can hold that droplet in place so when it goes out in the ocean, it doesn't also be coated by this ugly stuff. And so in these studies, to go back to what a surfactant does, if a soap molecule is one of these molecules that has a long oily tail on it and a polar head group on it, and the polar head group likes to be in the water and the oily tail goes into the oil, and it can break up oil in your clothes, for example, by simply the repulsive interaction between the head groups. But we have done a lot of studies looking at what these simple surfactants, safe surfactants, do when they go to that junction. And then more recently, the experiment that took nearly 4 years to get the laser to finally get the experiment to work, is then to actually look at them when they coat a tiny, tiny nanodroplet. So to find out what happens to the water, to find out what happens to the molecular structure of those soap molecules, and then see how strongly they hold that droplet together. And using surfactants as simple as some surfactants that are in ice cream. So very safe. And so we've learned a lot from these experiments about stabilizing these nanodroplets. And if you want a picture kind of what the experiment looks like, in this case, we have the laser beams go through a vial of tiny, tiny nanodroplets. That's why it's a little bit cloudy. And then we look at the light that is scattered off of those tiny droplets. Not the light that you see coming out that's bright, but the light that you can't see, which is about 1,000,000 times weaker than what you see coming out of there. That's why the experiments were so hard. But it's giving us a lot of detail about how these surfactants then encapsulate that little oil droplet and make it stable, and what factors go into making it stable. And remember I told you that we found out that it has this weak handshake with oil? We actually found out that these, just in the last couple of months, that for this little droplet, it hangs on even tighter when it's in this droplet form, as opposed to the planar form, which could be assisting in the stabilization of these nanomulsions. So beyond my own research, as I mentioned alluded to this morning, is I've also been very interested in some of the activities by Science Envoy for the United States to different countries, as well as through our Coach Women in Science programs. I've had the opportunity to talk to scientists all over the world, and everyone is concerned about water. Everyone is concerned about water, whether it be in the Mekong River region of Vietnam, where they're concerned about the fact that damming on the Mekong River by Laos and Cambodia is going to result in almost no water for their rice fields. That's going to hurt Vietnam, but 90% of the rice in Africa comes from Vietnam. So it's a global issue. Or going to Africa for our Women in Water project, whether it be Rwanda, Namibia, the first one to do the cleanup of water ever on the African continent, or North Africa, Casablanca, and also Tunisia. Water is a big concern everywhere. Or Oman, where they have coming up with ways in which they can use their deep seas that are very cold, bring the water up, and be able to have condensation then help irrigate strawberry plants. Or in Latin America, where water has a double-edged sword, where it can be as disastrous in hydrology with regards to mudslides with too much water or tsunamis. Women trying to help communities while they also do their geoscience. And in parts of Southeast Asia and Central Asia, where population growth is completely outstripping the ability to have clean water. You know, the hope is that as we learn more and more about water in any way that we can do that, the hope is that the more we learn, the more we'll want to know, the more we'll preserve it, and the more we'll cherish it.